calculations of how often by accident I would get this result, the answer is it's 2.8 sigma. Okay, you aren't going to get out of bed for 2.8 sigma. Same thing with this NVSS catalog. There we had more like 4 sigma, but these guys are at redshift of 0.14. So there is a possibility that there's a contamination by galaxies which are relatively nearby. That is not expected in the lambda CDM model, but the discrepancy you can argue away. So this was not definitive. So allow me to come to my punchline, which is this sky, where every little dot is a quasar. A mid-infrared quasar, which means you're really looking at the accretion disk around the central black hole, which is absorbing energy from the black hole radiation and emitting in the infrared. So all these are measured at various microns, 3.4 micron, 4.6. So these have different band names. Now we know that 99% of these are at redshift greater than 0.1, where they could have given us a clustering dipole, because we have measured a subsample of them. This was done not by us, but by the EBOS collaboration, and we are able to cross-match to our catalog and extract the redshifts. These redshifts are known to a very high precision, delta Z of 0.0002. So you better believe this. So we look at that, and then we calculate the dipole. You can even see it visually, right? And we know the spectra and the flux distribution of these quasars. So when we put it together, we find that the dipole, which is plotted here on this x-axis, is here for this cat-wise sample. Whereas the expectation from the kinematic interpretation of the CMP dipole is here. Why is there this spread? Because we simulate 100 million skies, and in each of them we draw the parameters at random from the known flux distribution and the spectrum of these quasars. So therefore we exactly duplicate our observational situation at random, and that tells us that this discrepancy, which has a p-value of 5 × 10⁻⁷, corresponds for a one-sided distribution to nearly 5 sigma. This is a gross violation of the cosmological principle and of the standard model of cosmology, which assumes that the rest frame in which matter is isotropic is the same as the rest frame in which the CMP is isotropic. And this gap is telling you that they are not the same. Okay, so I've now run out of time, so I shall ask for your indulgence to go to the last slide. If I can just get this guy to... Okay, sorry, please close your eyes while I fast forward through everything. I just wanted to show that the deceleration parameter is also anisotropic and therefore cannot be due to a cosmological constant, and that all the other evidence that people tell you is in favor of lambda is also consistent with no acceleration. The CMP does not tell us anything. We can come back to this in the questions. So let me come to my summary. The standard model of cosmology, as I remarked, was established only about 100 years ago. It actually, the lambda CDM model is only about 25 years old, but the mathematical basis for it goes back 100 years. Its foundations have never been tested because there was no data. But now we have data, we have a responsibility to test the fundamental assumptions and not just talk about precision cosmology of the parameters of this arbitrary model, which is unphysical from a fundamental point of view. What we find is that there is a dipole in the precession velocities of galaxies around us, and that tells us that we are in a so-called bulk flow, which is stretching out well beyond the scale where we expect it to have died out, and therefore we have not converged to the CMP frame. And the inference that the Hubble expansion is accelerating could just be due to the fact that we are not indeed the kind of observers that we are assumed to be. We are very, very untypical so-called tilted observers. And so what we see and infer as acceleration is not due to a cosmological constant at all. Most importantly, the rest frame of distant quasars is not the same as the rest frame of the cosmic microwave background. This is a body blow to the entire framework. We have to go beyond it. And fortunately, George Ellis and his collaborators have given us a manifesto going back to 1987 of how to construct a cosmology from observations. Remember, the cosmology that we used was not based on observations. It was based on the cosmological principle and the simplest possible options for the metric, for the matter content using Einstein's equations. Now I believe we should be empirical, we should build up a cosmological model from data, because that's what we do in modern science. And therefore, next time you hear a cosmology talk where somebody shows you what a great fit the lambda CDF model is, and how they are going to measure the equation of state of dark energy to the fourth place of decimals, you might like to keep this in mind. Thank you. I'm sorry I went over time, Chairman.
As it is already somewhat late, maybe one or two short questions. Also. Yeah.
Excellent talk, especially because it's a very powerful argument why the cosmological principle may not be right. But on the other hand, what I don't understand is this dipole, which you've so eloquently described, which is certainly giving us a directionality in space and time, is this possible to explain it away if you just sacrifice isotropy and homogeneity? I mean, do I know the cure for it? Is there a model?
There are many models. There's a book called Inhomogeneous Cosmological Models by a Polish cosmologist called Krasinski, who I met a few years ago in Warsaw, and I told him I'd never read his book. I never had to read it because we simply ignored it. Now I think we'll have to start reading his book. Okay. It is possible that the universe has a genuine directionality. We don't know yet. It is also possible that there is, I don't know, a long wavelength, isocurvature, superhorizon perturbation that gives us that. My task so far has been to just tell you what we know empirically. If I were Newton, I would say, hypothesis non-finito. It is for others to join us in this enterprise. We have to do a lot more. We would like to do tomography of this dipole. How does it change with redshift? To get some clues as to what the underlying reason might be. So we are right at the starting point. First, we need to get the community to accept that these questions are worth asking. The tendency in cosmology, as opposed to particle physics, is that any challenge to the standard model is jumped upon and brushed under the carpet. And I keep telling my cosmologist colleagues that in all particle physicists, in spite of the fact that we have such a good standard model working so well, we spend day and night trying to bring it down. Now that tells you something about the difference in the perspective of the two communities.
Thank you very much.
Yugen? Yeah, good.
This directionality you are talking about, is it local or?
No, it is not local. So initially we could only map out the universe to about a few hundred megaparsecs. That would be local. But these quasars are at a redshift of 1.2. That's thousands of megaparsecs, 10,000 megaparsecs.
Yeah, but even redshift of 1.2 is small, right? I mean, in the world of context.
In terms of distance, it's a long way. In terms of time, it's a long way. So, as I said, most of the universe that we know is only up to a redshift of 1. Of course, you can go to redshift of infinity, that is the Big Bang, right? But the region that we need for doing this test is redshift of 1 is more than adequate. In fact, more than 0.1 is more than adequate.
Okay, that's basically because you are trying to try one of the supernova data that's coming from.
That's part of it, but okay, I think I should answer you like this. In the standard model, the universe is supposed to be homogeneous when averaged on scales larger than about 100 megaparsecs. So if I go greater than 100 megaparsecs is enough. If I even go to 1,000 megaparsecs, it's enough. I should then have achieved the homogeneous universe for which I can frame this null hypothesis and then test it.
Okay, last question.
So, would your current observation, if you take it as granted, that the universe is not homogeneous and isotropic, at least on the order of magnitude as you have shown with the velocities come out, would that already give a qualitative explanation then would that already get rid of the acceleration?
Yes, well, what we find is that if we allow the inferred acceleration parameter Q naught to have a monopole and a dipole, so I'm parameterizing it thus. I'm saying it can have a dipole component and a monopole component, and I let my data speak. It picks out a direction in the sky, and the dipole is about 50 times bigger than the monopole. This scale is compressed compared to the vertical scale. So it tells me that the acceleration, in fact, let me show a map. So this is the dipole, this red and blue is the dipole in the acceleration parameter, if you like. Okay? And it's roughly in the same direction as the CAP dipole. But we only have 740 supernovae. With that, we can't reduce the absurdity bigger than that. And what we find interesting is that the original two collaborations that said that C acceleration, their supernovae were more or most in the same direction. This is a function of the telescopes on the ground that you look at the sky from. Okay? So there were about 100 supernovae in the original two studies. 15 of them were in common between the two collaborations. By the way, they disagreed on those particular 15 between them, but they are mostly in the same direction. So my question is, if they had looked in the opposite direction, I claim they would have seen a deceleration. Okay. So in other words, this question of which direction in the sky am I looking at, no paper will tell you that. We have to dig out these directions by cross-correlating with catalogs. They don't even tell you that. Because we are so conditioned to think that the universe is isotropic, we don't even bother to say that. Any more than you would report in your papers on Alice where you were standing in the lab when you took the measurement.
Same for lambda, so that's for the acceleration.
Yes.
Also explain lambda.
Well, lambda is inferred just from this. This is the direct measure of lambda. This is the direct measure of lambda because what we are doing is effectively. Sorry, let me just go back. This was something about the method used. So lambda is, as I said in the first equation, that is what gives you negative pressure, drives the acceleration. So what this is saying is that if it was lambda, it would be isotropic by definition. Vacuum energy does not have a directionality, right? So what we are seeing is definitely not vacuum energy. This is the point. It has got nothing to do with vacuum energy. The fact that the Department of Energy in the US now insists that anybody doing fundamental physics has to mention something about cosmology is got this mistaken belief that what you're seeing on the sky here has got something to do with fundamental physics. It does have something to do with fundamental physics, but not in the way that it is interpreted as the lambda vacuum energy of field. It's got nothing to do with that.
Okay, thank you, Shalin. Now we go for coffee break and we'll come back.